Okay, so we're going to go over the review sheet for the test on mean value theorem, second FTC, and accumulation functions. So the first two we want to try to do without a calculator. To find the average value of a function, you take 1 over b minus a times the definite integral from a to b of the function. So to do this without just popping it into the calculator, you need to first take the antiderivative, so that the x cubed, if you add 1 to 1/3, you get 4/3. That means you need to multiply the 8 by 3/4, and 3/4 times 8 is 6. And then if we take the antiderivative of 1, we get x. And we need to evaluate this from -1 to 8. So first, we're going to plug in the 8, then we'll plug in the -1 and subtract. So when we plug in the 8 cubed is 512 plus, well, to figure out what 8 to the 4/3 is, you take the cube root of 8, which is 2, raise it to the 4th, 16. 16 times 6 is 96. So first we plug in the upper limit, which is 8. Okay. And then we're going to plug in the -1 into the antiderivative. So that's -1 cubed is -1. -1 to the 4/3 would be the cube root of -1, which is -1, to the 4th, which would be +1 times 6. And then minus -1, so plus 1. So what we get is 1/9. Just trying to think. So if you add up everything in here, that would be 92. That would be 6. If we subtract 88 plus 512, oh, that's nice. That's 600 minus what's in here. That's just going to equal 6, so minus 6. And you could use your calculator for the arithmetic here. I just want to see that you use the FTC to get the antiderivative and that you're plugging in the upper, lower, and subtracting. And then, so this turns out to equal 66. So that's the average value of this function between -1 and 8. Okay, for the second part, for the second question, we want the average rate of change. For that, we use the slope formula. We're going to use f of 8 minus f of -1 over 8 minus -1. So you got to figure out what f of 8 is. You got to plug 8 into the original function. So that would be 3 times 8 squared plus 8 times 8 to the 1/3 minus 1. Then we'll have to plug the -1 in to get f of -1. So 3 times -1 squared plus 8 times -1 to the 1/3 minus 1. And then we'll have to divide everything by 9. So 3 times 8 squared, 3 times 64, that's 192. 8 to the 3rd is 2, because it's the cube root of 8, so times 8 would be 16 minus 1. Then over here, we plug -1 into the function. That's just 3 times -1 squared is just 3. The cube root of -1 is -1, so times 8 would be -8. And so we get 213 over 9. Okay, now, if you're asked the same thing and you have your calculator, it makes these much easier. So find the average value of 3 to the x from -2 to 3. So we need the 1 over b minus a times the definite integral from a to b of our function. That's the mean value theorem for definite integrals. So we get 1/5, but this time, because it says you can use your calculator, you can just plug the definite integral of 3 to the x negative 2 to 3 in your calculator. Let me just get my calculator out. Okay, so we're going to do math 9. Put that down here. Erase this. Math 9. We're integrating 3 to the x from negative 2 to 3. Oops. Just got to move that thing. Okay, so from negative 2, the upper limit is 3. And then what we're integrating is 3 to the x with respect to x. Now, the definite integral, we still have to remember we got to multiply this by 1/5 out front. So if I can get this, but I still have to multiply by 1/5, because remember it was 1 over b minus a. So I'll just divide by 5. That's the same thing. Divided by 5. And we can get our answer that way. So 4.895. Always round to 3 places after the decimal. So that would be our answer for that one. Now, average rate of change of this function. We're just going to use the slope formula. So we need f of 3 minus f of negative 2 over 3 minus negative 2. So this is going to be, f of 3 would be 3 cubed minus f of negative 2 would be 3 to the negative 2 over 5. We don't have to use our calculator in this one. It's not a big deal, but what the heck. I mean, it's 27 minus 1/9 over 5, but we'll go to the calculator. So we're going to take 3 cubed minus 3 to the negative 2. And we have to divide this by 5. Divided by 5. So let's see if this will convert. Probably not. Math 1. No, that's not going to convert. Oh, it is. 242 over 45. Oh, yay. Okay. So we can go back and just put our answer once we've shown that we know what to do. So 242 over 45, which is roughly, if you're going to use decimals, 5.378. For 5 through 8, you're just applying the second part of the fundamental theorem of calculus that says if you want to take the derivative of a definite integral function, its derivative of upper. So to take the derivative, you only do this to take the derivative of upper, which is 1, plug in the actual upper limit of integration in for all the t's. So when you do that, you'd have 1 times 2 sine x plus secant x minus 2x squared. Now, if there was an x in the denominator, in the lower limit of integration, then we'd have to do minus derivative of lower, plug in lower. But that would be 0 because the derivative of a constant is 0. So that's all we had to do for that one. For the next one, what we could do before we take the derivative is rewrite the function as negative the definite integral from 4 to x. Cosine of 3t plus cosecant t tan t. So now when you go to apply the second part of the FTC, you're taking the derivative. Sorry about that. Take the derivative. Well, first of all, we have a minus outside, so that's going to be minus outside the whole thing. So make sure you use parentheses. So derivative of upper, once again, is 1, plug in upper. So you're just going to get 1 times, which we're not going to write, cosine of 3x plus cosecant of x, tan of x. And that's it. You don't have to do drill lower because that'd be 0. Oh, great. Okay, we might have a fire drill, a fire bell go off. Okay, so the next one gets a little more interesting, but it's still the same thing. So to take the derivative of a definite integral function, that's what I'm calling them instead of accumulation function, so you'll remember. Derivative of upper. So the derivative of cosecant of u, if you remember, when you take the derivative of the cosecant of some angle u, it's negative cosecant u cotan u times u prime. So the derivative of upper would be negative cosecant x squared cotan x squared times 2x. That's derivative of upper, and you need to multiply that by what you get when you plug in the upper limit, the actual upper limit of integration, not the derivative, in for all the t's. So it'll be 3 cosecant of x squared minus the cosecant of x squared. And that's it. Again, we don't have to do minus derivative lower, plug in lower, because again, it's a constant. Its derivative will be 0, and 0 times anything is 0. So that's all for this one. Okay, the last one of these, this is the one that's got it all. Before we start this one, because we have to do derivative of upper, let's rewrite the sine squared of 3x as the sine of 3x squared. So now we go to get the derivative. Derivative of upper, we got to use chain rule on that. So to take the derivative of this, we're going to use chain rule. So we start with the outermost function. So 2, leave the inside alone to the first. 2 sine of 3x. So we took the derivative of the squaring. The next function in is the sine. The derivative of the sine of an angle is cosine of that angle. Then you got to multiply by the derivative of the innermost function, which is 3. So all that is derivative of upper. Now we got to multiply that by what we get when we plug in the upper limit in for t. So I'm just going to move this over. I'm going to try to fit this. So this times, I'll use a different color. It'll be tan of sine squared of 3x plus sine squared of 3x cubed minus 2. So far, we have derivative of upper, limit of integration, plug in upper, minus, now we got to do the same thing with the lower limit because it has an x in it. The derivative will not be 0 again. So minus derivative of lower, well, the lower is square root of x, which is the same as x to the half. So the derivative would be 1/2 x to the negative 1/2, which is saying we can leave it like that or write it as 1 over 2 rad x. So minus derivative of lower, which is 1 over 2 rad x, times what you get when you plug in the lower limit in for all the t's. So times the tan of rad x plus rad x cubed minus 2. And that whole big mass is the derivative of this accumulation function. Okay, now we get to the fun stuff. Next problem, we're given a function h of x that's defined to be the definite integral from 1 to x of f of t. And what we're looking at, they tell us, is a graph of f. Right, the graph of f is over here. So this is f. First thing you do with this type of function, when a function is defined as a definite integral, take the derivative using what we just did. Right, derivative of upper is 1 times what you get when you plug in the upper. So it'll just be f of x. So when they tell you that this graph here is the graph of f, realize that is equivalent to the graph of h prime. Now we can start. To get the value of h of 0, you have to use this definition, right? So according to that, I'll write it up here, h of 0 equals the definite integral from 1 to 0 of what you're looking at. Well, if you're going to have to get the value of a definite integral from the graph using areas, let's make that lower limit left. Let's switch them so that h of 0 equals negative the definite integral from 0 to 1. Now, to get that definite integral, we just have to look at the graph between 0 and 1, and we got to figure out what is the area above minus the area below. Well, if you look at the area between 0 and 1, okay, when I say it's the area between the graph and the x-axis, notice that that area is above the x-axis. There's no area below, so area below is just going to be 0. I don't have to worry about that. Area above is the area of this triangle. And the area of a triangle is 1/2 the base, which would be 1, times the height, which would be 2. So that equals 1. So area above is 1, area below is 0. So the definite integral from 0 to 1 of this function is just 1, but remember, we got to multiply it by -1. So h of 0 equals -1. To get h prime of a value, well, you're looking at the graph of h prime. So h prime of 0, we're just going to look at the graph. So h prime of 0 is the y-coordinate on the point of y equals h prime of x when x is 0. So that's just 2. Reading the graph. The second derivative is the derivative of the first derivative. It's the slope. Remember, guys, whenever you think derivative, it's the same thing graphically as saying slope. So now I got to figure out what's the slope of h prime when x is 0. Well, when x is 0, let me just erase that. Right here. Well, to figure out the slope at this point here, because this is part of a line, the slope of a line segment never changes. So the slope here is the same as the slope here, here, here. You can just figure out the slope using any 2 points. So if you use, let's say, this point and this point, you see change of y's over change of x's. The slope, it's down 2 over 1. The slope is -2. Now, if you need a formula to do that, just you look at the coordinates of each point, right? And you use the change of y. So let's take this y minus that y. So 2 minus 0 over this x minus that x. So 0 minus 1. So the slope of g prime at any point along this line segment is -2. So including at 0, the slope would be -2. When it comes to finding zeros of these, you always start out by finding out if there's a value of x that makes the lower limit of integration equal the upper limit of integration. Because h of in this case 1 would be the definite integral from 1 to 1. Yeah, that would be 0. So you know for sure that h of 1 is 0. That's how you figure out if they're, what the first 0 is with these. To get any other value, what you're trying to do to see if there are any other roots is ask yourself, is there any other number, x, where if I were to look at the area between the graph, between 1 and that number, where area above minus area below would be 0, right? Because that's how you would find h of a number. So what you do is you look, starting here at 1, if you look right, if I just keep going right, nope, area above minus area below between 1 and any of these numbers is never going to be 0, right? So I won't get a 0 over here, but now let's go the other way. Let's see if we start at 1 and we go the other way. If the definite integral would be 0. If area above, starting at 1, to any other number, area above minus area below, would that ever balance out? No, because even though you start going negative, you don't ever get enough area below to balance out. So there are no other zeros other than the 1, the first one that you got. Okay. Now, this part is the big part, because here, to get values of h, we have to use the definition. All right, so we need to get areas, because to get any value of h, remember, we have to take the definite integral from 1 to x, whatever the number is, of this, f of t. And so we need to get areas. And since we're going to have to get a bunch of these, let me just see which numbers we're going to have to break it up at. So -5, -3, -2. Okay, 1. Well, that one we know, 3 and 5. All right. All right, so why don't we just start by filling in the area of all the shapes between the x-axis and the graph. So the area of this triangle down here is 1/2 base times height. 1/2 2 times 4 is going to be 4. Let's get the area of this next region. Between -3 and 2, the area between the graph and the x-axis, 1/2 base, which is 1, times height. 1/2 1 times 1 times 4 is 2. Let's do this rectangle. You can count them or just say base times height. There's 4. Now we've got, I don't think I have to break it up at 0. Let me just see if I need to break this up to a trapezoid and a triangle. Nope, I don't need h of 0, so might as well just do the whole thing all at once. So 1/2 the base times the height. 1/2 2 times 4. That's 4. Now, I do think I have to break it up at 3. Okay, since I have to break it up at 3, I'm just going to break this up. Well, this would be, you know, if you drew the whole circle, the radius would be 2. So the area of the whole circle is always pi r squared. So the whole circle would be pi times 2 squared, or 4 pi. So that would mean that each quarter of this circle would be 1/4 of that, or just pi. So there's a pi, and there's a pi. Once you have all these areas, now answering the next part becomes easy. So you always start with the definition. So h of -5 is equal to definite integral from 1 to -5 of f of t dt. We're going to switch them and use the area. Remember, if you're using the area to get a definite integral, the lower limit has to be less. So it's negative the definite integral from -5 to 1. Now we look, so the answer is going to be negative. We've got to look at the graph between -5 and 1. So between -5 and 1, area above looks like it's 10, right? Because you have the 2, the 4, and the 4. Area below equals 4. So the value of the definite integral from -5 to 1 is 10 minus 4. 10 minus 4, which would be 6, but remember, we had to multiply by a negative. We had to switch them, so we get -6. Now we got to take, to get h of -3, again, we're using the definite integral. This is just the definition of how this function was defined, so we're plugging it in. So that would be the definite integral from 1 to -3 of f of t dt. So once again, we got to switch the limits of integration. Then we can use the area. So when you switch limits of integration, right, we negate it. Now we'll look at the graph between -3 and 1. I just don't want to forget that we got to put a negative out there. Okay. So between -3 and 1, we're going to do area above minus area below. -3 and 1. Well, all the areas above. Area below is 0. So the definite integral of this function f would be 2 plus 4 plus 4, or 10. So we get negative 10, negative 10, because area below was 0. I didn't have to subtract anything that time. Okay, definite in h of negative 2 is a definite interval from 1 to negative 2. So we switch them, which means we got to negate. So it'll be minus the definite interval from negative 2 to 1. Now we just got to look at our graph between negative 2 and 1. And again, we're going to do area above minus area below. Between negative 2 and 1. Oh, it's all above again. So it's just 8, right? The area between the graph and the x-axis is just 8. Area below is 0. So you don't have to write 8 minus 0. So we get negative 8. Finally, we get to an easy one. H of 1 is the definite interval from 1 to 1. Well, even if I didn't look, we would know that that's 0. H of 3 is the definite interval from 1 to 3. So we don't have to switch it this time, right? Because now the lower limit's less. We look at the graph between 1 and 3. Between 1 and 3, area above is 0, area below is pi. So the definite interval from 1 to 3 of f is negative pi. So area above minus area below, negative pi. And finally, h of 5 is equal to the definite interval from 1 to 5. So we got to look at the graph between 1 and 5. It's all below this time. Area above is 0. Area below is 2 pi. So that equals area above minus area below equals negative 2 pi. So that's probably the hardest part of when you're given the graph of an accumulation function, a graph, which is basically the derivative. You need to plug the number into the function, which means evaluating a definite integral, which means finding all the areas. Okay, D. Okay, we're looking at h prime. It says at what values of x does h have a relative min? A relative min occurs when the derivative, h prime, changes from negative to positive. So you're looking on the graph, where does the derivative change from negative to positive? And that's going to happen at negative 3. Right, so that's what you would say. It has a relative min at x equals negative 3 because h prime changes from negative to positive. Okay, next part. On what intervals is h concave up? Well, we know h is concave up when the second derivative is positive. And that, again, you got to relate it back to the first derivative. So that means we got to look to see where the first derivative is increasing. And you don't have to write d of x. You can just write h prime is increasing. So you want to find where h prime is increasing. So when you're looking at your graph, so it's increasing from negative 5 up to negative 2. Remember, when you're giving intervals of increase or decrease, any intervals, it's the x coordinates. So you see it's increasing wherever it's going up as you read it left to right. So you want to say from negative 5 to negative 2. We really should include that negative 5. And it doesn't matter whether you want to, I guess we could include, it doesn't matter whether you include the negative 2 or not. But yeah, you could. It's up to you. Yeah, I'm just going to write this, or negative 5 to negative 2. Because when you say a function's increasing, that means if you take any 2 points, the y-coordinate of the point on the right is greater than the y-coordinate of the point on the left. So even if you included the negative 2, right, it's true if that was one of the points and you chose any other point, the y-coordinate on the right would be greater than the y-coordinate on the left. So I think that's actually a better answer. Okay, then F, At what values of x does h have a point of inflection? Well, we know that's when the second derivative changes sign. And we know the second derivative is just the slope or the derivative of the first derivative. So we got to look where the slope of what we're looking at, h prime, changes sign. So that's going to happen whenever your function goes from increasing to decreasing or decreasing to increasing. Now we look at our graph. You know, your function, it's increasing, but it's not changing to decreasing, right? It's constant. So -2, we're not going to have a point of inflection on h at -2 because the slope is not actually changing sign. All right, this is not a relative max. That's another way of looking at it. Same thing here at -1. The slope is going from 0 to negative. All right, to be a point of inflection of h, the slope of h prime, the second derivative, has to go from negative to positive or positive to negative. One of them can't be 0. So far we don't have one. Then our slope is negative, and it's still negative until we get to 3 here. Now the slope is changing from negative to positive. So we would have a point of inflection on h at x equals 3. Okay, going to the next one. Last one. Oh, I didn't label my points. Let me do that quickly. Let's see. We have the point up here, which is 4, 3. You're given that this point is 6, -3. And this point up here is 8, 3. That's 1, 0. And down here we have -1, -2. And over here starts at -2, 0. Okay. It's a graph of g prime. So this is one of these where they tell you, oh, this is the graph of the derivative. For this type, if they're just going to say it's a graph of the derivative, the only way you're going to be able to get values of the actual function is if they give you a starting value. So it says, what are the roots of the function? Well, they actually gave us one of them, didn't they? They already told us that when x is -1, the function g equals 0. So we already know that when x equals -1, g of -1 is 0. So that's a 0. Now, any other value, if we want to get g of any other number, okay, to get values of g of x, we're going to take the y value that we know, g of -1, and add the change in y, which we're going to get by integrating g prime from -1 to 0. So to get values of g of x, it's going to be g of -1, that's 0. Okay. Oh, wait, I didn't say, why did I say, I didn't mean to 0 up here. It should be to x. Sorry about that, kids. So if you want g of x, you start with g of -1 and add the change in g by integrating the derivative of g from -1 to whatever x is. And g of -1, remember, is 0. So for this function, g of x is going to equal the definite integral from -1 to whatever x is. So we want to know, is there a number, if I take the definite integral from -1 to that number, will I get 0? So you want to look at your graph between, because you know g of -1 is 0, okay? Starting at 0, if you go left, area above minus area below will never balance out. So we will not have any zeros to the left. But now let's say we start looking at values of x to the right. If I take a number, I'm looking to see when between -1 and some number will the area above and below ever cancel each other out. And yeah, that's going to happen right here. Because if you took the definite integral of g prime from -1 to 3 by doing area above minus area below, you would get 0. So that means that x equals 3 would be another 0 of this function. So that's a 0. So we can start from this point. Now, let's see what we would get here. I got to look at the areas, make sure. Let's see, the area of this little piece in here. So your function now, g, that you can't see, is still increasing. The derivative is positive. This area in here of all this, you can see is 2.5. So now g is increasing. It's going up by 2.5, and then it goes up again by 1.5. So by the time you get to x is 5, g of 5 is 4, way up there. I can't even graph it. Then it does start to decrease because the derivative is negative, but let's look at the amount of decrease. Because the amount of decrease is just whatever this area is below. So our function goes from 0 up to 4, and then it's going to go down by 1.5, so it would be back down to 2.5. Then it would go down another 1.5, so it would be down to 1. But then it's going to start going back up again. Because now the derivative is positive, it's starting to go back up by 1.5. So it's never going to get back down to 0. And to help you kind of see this, so the actual function g, we know it was 0 here, right? It is going to go down. I just want to like sketch the graph. I think this might help you. I'll do it in blue. Okay, so it was 0 here. It's going to decrease by this area here, 1/2 base times height, so 1/2. So your function that you can't see goes down 2, right? Because this, it's going to decrease. Derivative's negative by this amount of area. So it's going down by 2. Now it has a relative min, and now it's going to go up by, well, this is 2 also. So one will go back up by this area, and I know it's going to increase because the derivative is positive, so it increases by 2. That's why it's back to 0 at 3. But then between 3 and 5, the graph of my function is going to increase by 2.5. This is like a hard thing. And then it's going to keep increasing by another 1.5. So it's going to get all the way up to the 0.54. I'm using the areas to figure out how much it increases by. Now it'll have a relative max. You can see how the derivative goes from positive to negative. But now the derivative is negative between 5 and 7. So now your function's going to start decreasing. It's going to come back down, but it's only going to come down 3. So it's going to come down here. So it's going to come, let's see my shadow here. So it's going to come down to 1, but then, oh, I should have made the concavity different. That don't worry about so much. Okay, it's going to come down to 1, and then it's going to go back up another 1.5. So it'll go up to 2.5. Oh, I went up a little too high. All right, so that'll help you as far as seeing, okay, where would the zeros of this function be? All right, so they gave us 1, and then we had to think about how we'd get the other values, and we'd realize it would be the definite integral from -1 to x. And you know what? I didn't draw the graph over here. This area in here is 1/2 base times height is 1. If you read this left to right, that function had to be increasing, I'm sorry, it's negative, decreasing by 1 to get to 0, right? So that means it must have been up here at 1. That's very nice. Okay, so now in blue you can see what the actual function looks like. You don't have to do that for this, but it just helps you to see, you know, you already knew when the derivative was negative, the function was decreasing. When the derivative was positive, it was increasing. But now you also know that the amount of increase or decrease, the amount of change, is just going to equal the area between the graph and the x-axis. Okay. Next one. Where on the interval from -2 to 8 is g decreasing? So we should be looking for where g prime is negative. So it's negative, and let me erase all this other stuff. I might want the areas here. You know what, I'll just leave it. Okay. So the graph of g prime is negative between -2 and 1, and between 5 and 7. And yeah, you could definitely include the endpoints, as again, like I said, because when you're talking about intervals of increase or decrease, so what did I say? You know, but then there are other people who are always saying, oh, you know, just strictly when it's negative. So either way, when the derivative is 0, if you want to include it where the derivative is positive or negative, you can, because we're talking about intervals of increase or decrease. But if you want to strictly stay by the book, functions decrease when the derivative is negative, using the graph, we could say from -2 to 1. Again, if you use the brackets, it's okay. And then again, from 5 to 7. All right, so functions decreasing when derivative is negative. Next part. Where is the absolute max of g? For an absolute max, you have to figure out the value of g at the endpoints. So that's -2 and 8. And for an absolute max, it could occur at an endpoint or where the derivative changes from, for a max, positive to negative. And if we look at the graph to see where the derivative goes from positive to negative, that occurs at x equals 5. It's just one value we got to consider. Now, to get values of g, we got to work off that starting value. So to get g of -2, we're going to start with g of -1, which is 0. And now the change by taking the definite integral of g prime from -1 to -2. So we'd have to switch them. The g of -1 is 0, so we have 0 minus the definite integral from -2 to -1. And if you look at your graph of g prime, between -2 and -1, area above is 0, area below is 1. So the definite integral from -2 to -1 is -1, but again, we got to multiply it by -1, so we get +1. So 1 is the value of g at -2. To get g of 5, again, we started g of -1, which is 0, and now the change from -1 to 5 by integrating the derivative. So this time we don't have to switch the limits of integration. Lower limits less. We look at the areas from -1 to 5. So the area above, so I'm going to do all the area above and then subtract all the area below between -1 and 5. So if you add up the area above, we have, let me go back to that last screen. 2, 2.5, that's 4.5, and another 1.5, that's 6. And then the area below would be 2. Okay. So let's go back here. Oh, no, right here. Okay, so for this one, we're finding the definite integral from -1 to 5 of g prime. So we just looked at it. Area above was 6, area below was 2. So we get a value of 4. for g of 5 equals 4. And finally, we got to get g of 8. So again, we'd start with g of negative 1. That was the point we were given. We'd add the change from negative 1 to 8 by integrating the derivative. So now we got to look and do area above minus area below between negative 1 and 8. So the area above, if you look at this, I'm going to go back to that other one. We already had the 6 in here, and now we have another 1.5. So we have 7.5 above. Let's write that down. 7.5 minus the area below. So, and this was between negative 1 and 8. So here we have 2 below, right? And over here we have another 3. So we have a total of 5 below. So the definite interval from negative 1 to 8 would be 7.5 minus 5, which would be 2.5. Area above, which is 7.5, minus area below, which we said was 5. And this is going to equal 2.5. Okay, so now you have the y values of this function that you really can't see at the endpoints and where the derivative changes from positive to negative. So we're looking for the absolute max, so we compare the values, 1, 4, 2.5. The greatest of these is 4, so the absolute max is 4, and it occurs at x equals 5. Yeah, they just said where is it, so you only have to give the x value. So the absolute max occurs at x equals 5. But what you always want to do for a justification with this type of problem is make a statement in the beginning, absolute max can only occur at an endpoint or where the derivative changes from positive to negative. Okay. Part D, write the equation to the tangent line of the tangent line to the graph of g at 5. So y minus, we need to plug 5 into the function to get y1. We need to plug 5 into the derivative to get the slope. G prime of 5 is the easiest one. You just read the graph. So if you look at the graph, G prime of 5, that's 0. Okay. So we have that. X minus 5. So the only thing we have to get now is g of 5. We got that somewhere back there. Yeah, in the last problem. Remember g of 5 we figured out was 4. So y minus 4 equals 0. Or we can write this as just y equals 4. To write the equation for g, explicit equation for g, so we want to know what g of x equals. But we're only talking about x values between negative 1 and 4. You have to start out by writing the equation for what you're looking at, g prime of x. So if you look at g prime of x, let's look at the graph between negative 1 and 4. So this is the graph of g prime. So you notice what we're looking at, g prime is linear. To write the equation of a line, there are two ways. You can use y equals mx plus b, or you could use y minus y1 equals m times x minus x1. Now I'll show you both ways in this one. If you wanted to use, well, either way, you're going to have to get the slope. To get the slope, you need to take 2 points that you know are on it and do change of y's over change of x's, right? So this graph, if you label this point here, this is 4, 3. This point is 1, 0. So to get the slope of this line, difference in the y's over, in the same order, difference of the x's, you get 1. So the slope of this line is 1. So no matter which way you're going to write the equation of this line, sorry, just want to fill this in. You're going to have to fill in the slope. So now we figured out the slope is 1. So it's here or here. Now, If you want to use y equals mx plus b, you have to have the luxury of knowing where the line crosses the y-axis. Well, here we do. It's -1. Right? So b is -1. So the equation of that line is y equals x minus 1. The other way, if you didn't know where it crossed, you could pick any point on it. Let's take the point 1, 0. Plug in the x-coordinate in for x1 and the y-coordinate in for y1. And when you solve for y, you still get y equals x minus 1. So the equation of the derivative, g prime of x, is just x minus 1. That's what we had to start with. So before we can come up with an equation for g, we first write an equation for what we see, which is g prime of x, which is x minus 1. Now, to go from g prime to g, just take the antiderivative. The antiderivative of g prime will get us to the function g. So we get 1/2 x squared minus x. This is not a definite integral, so we need a plus c. To solve for c, you need to know one point on the graph of g where the x value is between -1 and 4. So looking back at the work that we have, well, we know several of them. We could use the fact, these are points we can use, because it has to be a value where like we already know g of -1 is 0, right? We know g of 3 equals 0, so I could use that point. We could even use g of, what's another one here? G of, now I can't use the 5 now. All right, so if the ones we had, we don't want to do extra work to find other values of g. Let's use one of those. So I'll use this one. So I'm going to plug in 0 for g of x, and I'm going to plug in 3 for x, and solve for c. So we get 0 equals 9/2, which is 4.5, minus 3 plus c. So 0 is equal to 1.5 plus c. So that means that c is equal to -1.5. So now we can actually fill in that value, go back up to g, right? Fill in that value, and we have our equation for g of x. So g of x, function we can't see, on that part anyway, its equation is 1/2 x squared minus x. You can write either -3/2 or -1.5. All right. Then the last part, what is the average value of g prime on the closed interval from 1 to 8? So they want the average value of g prime. So we know we're going to have to use 1 over b minus a times the definite integral from a to b of that function. So we're going to get, so that's just the mean value theorem. That's how we started this whole review. We're going to get 1/9. To get the definite integral from 1 to 8 of g prime, we're going to have to look at the graph between 1 and 8 and do area above minus area below. So let's look back at the graph. We're only looking between 1 and 8. I'm just going to fill in the areas we had. So let's see, that was 6.5. Oh yeah, this was just 1/2 base, which was 4. So 1/2, let's write that, base times height. So the area of this up here is 6, and the area of this 1/2 base times height is 3/2. So I'm just going to write 1.5. So, oh yeah, we did this before. So area above is 7.5. Area below, the area of this triangle is 1/2 base times height. Okay, 1/2, 2 times 3 is just 3. So the definite integral from 1 to 8 of g prime is going to be 7.5 minus 3. So area above minus the area below. So that would be 4.5 if we subtracted. So 1/9 of 4.5, or 9/2. Oh, 8 minus 1 is not 9. Sorry, kids. I was thinking the last problem was 8 minus -1. So that makes a difference. So it's 1/7 times 4.5, or 9/2. So we get 9/14 for the average value of G prime. Which, if you were interested, the average value of G prime would be equivalent to the average rate of change of G. Because if you took the antiderivative of G prime, this is a slide thing, you don't have to do it this way. The antiderivative of G prime would be G, and you would plug in the 8 and the 1 and subtract, so you would get 1/7 G of 8 minus G of 1. So it equal the average rate of change of G. But I hope I didn't confuse you with that. You could just do it this way. All right, I think that's it. Bye.